All right, let's jump straight into this explainer and build your ultimate toolkit for understanding kinematics. Look, if you've ever watched a car speed up down a highway or maybe dropped a tennis ball off a balcony and wondered exactly how the math works behind those movements, you're in the right place. We're going to decode the physics of motion today, and honestly, it is incredibly satisfying once you've got the right tools in your hands.
So here's the big question we're looking at today. How do we mathematically predict the future of a moving object? If we want to know exactly where a car will be in 10 seconds, or how fast it's going to be going when it crosses a finish line, we need a rock-solid system to predict reality. We aren't just guessing here, right? We're using concrete mathematical frameworks to map out what will happen in the physical world literally before it even occurs. Here is our roadmap for today. We're going to meet our key variables, check out the 5 SUVAT equations, visualize the math, map out their connections, and then apply them to some real-world cases.
Okay, part 1. Let's meet the key variables. Before we build anything, we have to lay down some ground rules. The absolute golden rule here: the physics we're about to dive into only applies if the acceleration remains absolutely steady. That means our acceleration, which we call A, literally cannot change in magnitude or direction. Think of a smooth, steady press on the gas pedal. Swerving wildly or pumping the brakes? Yeah, this specific toolkit won't work for that. Constancy is the whole secret sauce for everything we're about to do. So meet the SUVAT squad. SUVAT is just a super handy acronym for our 5 main variables. We've got S for displacement in meters. U is our initial velocity, and V is final velocity, both in meters per second. Then there's A for that constant acceleration we just talked about in meters per second squared. And finally, T for time measured in seconds. And hey, quick pro tip. Always check your SI units before you start crunching numbers. It's your first line of defense against making a really frustrating mistake.
Moving right along to part 2, the 5 SUVAT equations.
Now, check out how this all comes together. These aren't just random formulas thrown on a page. They're an interconnected family. You can actually map them out like a pentagon. Up top, we have equation 1, v equals u plus at, finding your final velocity. Down the sides, we see the displacement variations, like s equals ut plus 1/2 at squared. What this map is really showing us is that every single equation just uses a slightly different combo of our SUVAT variables to cover any possible blind spots in our knowledge.
So how do you actually use these out in the wild? It's basically a matching game based entirely on what you have and what you're trying to find. Step 1, just take a quick inventory of the variables you already know. Step 2 is a brilliant little shortcut. If the time variable is nowhere to be found in your problem, just jump straight to equation 3. V squared equals u squared plus 2as. It's the only one that completely ignores time. Then step 3 is just some basic algebra to rearrange things and solve for your missing piece. Easy as that.
All right, part 3. Let's visualize the math.
Let's see what this algebra actually looks like as physical shapes. Think about a velocity time graph. It gives you this straight angled line, and the exact slope of that line, that's your constant acceleration. And since it is constant, an acceleration time graph is just a perfectly flat horizontal line. But what about displacement? Because we've got squared time variables in those formulas, that graph sweeps up into this really beautiful curved parabola. But here's where the geometry gets incredibly cool. Look under the sloped line of that velocity time graph. You'll see it forms a trapezoid. If you calculate the geometric area of that trapezoid, just average the initial and final velocities and multiply by time, you're literally deriving equation 4 for displacement. It's wild. It's like math and geometry are telling the exact same story, just in 2 different languages. Which leads us perfectly into part 4, deriving the connections.
Let's take a quick peek behind the curtain here. We can actually mash equation 1 and equation 2 together to magically create equation 3. If you mathematically isolate t in the first formula, you can inject that straight into the second one. Once you simplify the algebra, the t just vanishes completely. This just goes to show that all these formulas are built from the exact same foundational DNA.
Finally, part 5, real-world special cases. Let's take this out on the road. Now, zeros? Zeros are a physicist's best friend. If a car launches from a dead stop, your initial velocity, u, is 0. So massive chunks of your equations just disappear, leaving you with these clean, super compressed formulas. On the flip side, what if you're coming to rest at a red light? Your final velocity, v, is 0. That lets you rearrange the math specifically to figure out your exact stopping distance.
And what if you're just cruising on an empty highway, foot steady on the pedal? You've got zero acceleration. The math slims right down to basic distance equals velocity times time. But if you hit the brakes, that's negative acceleration. The formulas don't change at all. You literally just flip the sign on your A to negative before you run the numbers, and you're good to go.
So, as we wrap up this explainer, keep these 3 golden rules in your back pocket. First, really grasp what each variable physically represents in the real world. Don't just treat them as letters on a page. Second, use whatever variable is missing to pinpoint the perfect equation. And third, I absolutely cannot stress this enough, always double-check those SI units before you hit calculate.
Think about what we've covered today. You now literally possess the tools to mathematically predict the physical future of a moving object. So next time you're out and about, look around. Whether it's a jet taking off or just a leaf falling from a branch, what physical reality are you going to decode today?